The purpose of this video is to look at goal 12 of our inference unit, which says that we want to be able to do a hypothesis test of a mean using what's called a one-sample t-test for the mean. Make sure before you watch this that you really understand that t-distribution and the conditions that are necessary to use it. All of that is in the video with the one-sample t interval. So make sure you understand all those concepts, because I'm not going to really explain any of that here. We're just going to go ahead now that hopefully if you understand the t-distribution, we can just go ahead and use it to do a hypothesis test. Now, we did hypothesis tests for one proportion and for the difference of proportions. So this is very similar in structure to the one proportion z-test. The main difference being, instead of looking for a hypothesized proportion to test against, it's just a hypothesized mean. And since we're using means instead of using a z-score, z-test, we get that t-distribution, and we have to use a t-test. All right. So if you're aware of those differences from the other video, then hopefully this will make sense. It's very similar in process. All right. So I'm going to use the example from the confidence interval video on sample means to take a look at this test. So basically it's going to be the example where the cars were going past the school. All right. So in that last video, I gave the information where there was a bunch of cars going by the school. We wanted to know in general if they were speeding. We just took a random sample of 23 of the cars. That way we didn't have to sit out there all day or all year and test every car. So a random sample was taken of 23 cars. We found that they had a mean speed of 31, which on average looked like they were speeding. But once again, due to natural variation, that doesn't mean the entire population was. And that sample had a standard deviation. Oops, I have standard error in here. Let's fix that. So the standard deviation for the sample was 4.45 miles per hour. So in a test, because when in the confidence interval, we were looking for, is there some interval we could make that captured the real value with a certain level of confidence of how fast the cars were actually going. The sample's at 31, but once again, due to natural variation, the entire population may not be going that speed. So last time we made the confidence interval. What a test does, remember, is it tests against a standard. So we want to know if this is significant evidence that the real mean of the cars is over the posted speed limit. So 23 of the cars average 31. Is this indicative that the entire population of cars is really going over 31? Now, from our confidence interval video, at 95% confidence, we seem to think it was possible that they were under 30. If you remember, the low end of the confidence interval was somewhere like 29 something. All right. So since that confidence interval didn't seem to support it, the test won't either. But I want to show you how to do the test using a very similar example. So in our test, we're going to need certain pieces of information like what the normal state of affairs is. We'll have to check the conditions, and that'll show you how to make the calculation and the conclusion. And all of the steps follow very similar to the other hypothesis tests that we were doing. So let's look at the key ideas of the one sample t-test for the mean. That's its fancy name. So when you go to do a test for a sample mean, H naught, which is your null hypothesis. Remember, the null hypothesis represents the assumed or regular, normal, whatever you want to call it, state of affairs, which is symbolized by mu naught. So this is our hypothesized mu. We're saying we think mu is this value. We're going to assume it's that value and see what happens. So that's what this says. We'll assume that the population mean is actually our null mean. So it's an assumption we're going to make and see what happens under that assumption. So to test, we'll see how far our sample mean is from our hypothesized mean by getting, instead of a z-score, because that's usually how we've done it, we actually get a t-score. So this is called the test statistic. This is the structure of the thing they give you on the exam. So this is the exact same formula as we would have gotten for a z-score. It's just we're using a t-curve. And remember, the t-curve is a slightly distorted version of the normal curve. So to get the test statistic, which will give us our p-value, which will let us know if we're going to reject or not, the test statistic is t with n minus 1 degrees of freedom. So remember, the n is the sample size. So we just take the sample size minus 1, and that's the t-curve we make. And remember, the calculator will do that for you if you know how to tell it. And then we just get what we call a t-score instead of a z-score. Basically, the t-score is how many standard deviations away are we. Well, you take your mean that you found, your sample, subtract it from the hypothesized mean to see how far it is, and then divide by the standard error. If you do that, it tells you how many standard deviations you are away from that hypothesized mean. Now, if you're close to the hypothesized mean, what that tells us is the null hypothesis is probably true. You're within variation, within reasonable variation where the null hypothesis seems like it's okay. If this comes out really high, if this is if your sample mean is many standard deviations away from your hypothesized mean, that's usually indicative of the fact that our sample's really unusual given our null hypothesis. And usually if we get something that's extremely unusual, we tend to think our null hypothesis isn't true. And that will give us a low p-value. So this is basically going to be like our z-score, and then we'll use it to get the p-value. High p-value, we won't reject the null. Very low p-value tells us the null's probably not true and we reject it. So once you get this value, use the t-score for n minus 1 degrees of freedom to get an area. And the area is our p-value, or you might have to double it if it's a two-sided test. The one I'm going to do is a one-sided test. All right. So once we get that t-score, it gives us the p-value, and the p-value is what we need to decide where we're going to reject our null hypothesis or not. Now, the way we're going to get the area is just like you used to use normal CDF. Since this is a t-curve, I'll show you on the calculator, there's something called t-CDF. It does the exact same thing. It basically gives us the amount of area on the t-curve, and we use that to get our p-value. Now, I wanted it all to fit on the board, so I'm going to check the conditions verbally, because basically in the last video, we already talked about these conditions. So if you haven't seen that other video, once again, make sure that you understand the conditions that are necessary. And this example, I had already checked the conditions. I'll very quickly just re-talk through them, but if you've seen that video, this should look familiar. So to check the 4 conditions, the first one is independence. In general, the speed of one car shouldn't affect the other. Remember, the only caveat I made on the other video was in the event that there's high traffic, if it was really busy traffic, someone who wanted to speed might not be able to speed because of the person in front of them. So we would have to be careful to make sure independence was met. And I mentioned it's probably the Reynolds Road outside the school. In general, that's never super busy where I think someone would get backed up too much. All right, so we'll assume that independence is met. Randomness, they tell us in the problem they randomly selected them. The 10% condition, 23 cars is way less than 10% of all cars that drive by the school. And that new condition from the other video is the nearly normal condition. Now, that nearly normal condition was based on the sample size. If the sample size was bigger than 40, we didn't really have to check anything. We just had to say, hey, the n's bigger than 40. In this example, the n is 23. So remember, if the n is less than 40, you'll want to look at a histogram of the original data. Someone needs to either let you know the original data is roughly normally distributed. If the distribution of the original data is kind of bizarre, not unimodal and symmetric, that can cause problems if the n is too small, because we need that central limit theorem to kick in, which was mentioned some videos ago. All right, so since we're under 40, I would have to check the distribution. From the other video, I already showed you the distribution was roughly unimodal and symmetric, so the nearly normal conditions met. Even though our sample size is on the lower side, the original data is normal enough to make our sampling distribution be pretty close to a normal AK, or rather a T-curve. All right. So the conditions are met on the board. I'm going to assume the conditions are met and not write them out. But you would, if you were actually doing an actual test, unless someone tells you otherwise, make sure you write out the conditions. If the conditions are met, after you're done, you would say, due to the conditions being met, I'm going to perform a one-sample t-test for the mean. All right, so the test itself. Now, if we were in class, I would do it out, but since we're not, it's back here. All right, so I have the 4 steps of the hypothesis test. Step 1 is to make your hypotheses. So the null hypothesis is that the population mean is 30. So remember that the null hypothesis is the normal state of affairs. Since the speed limit is 30, we're going to just assume that everyone is going the speed limit and then see if our samples suggests otherwise. So our null hypothesis is the normal state of affairs. That's that the cars are really okay. They're doing the speed limit. Now we're doing a one-sided test because we wouldn't really care if they were going under the speed limit, because these are people who worry about school safety. So if people were going under the speed limit, no one would really be too concerned. So we just want to test if the real population speed is greater than 30 miles an hour. So that's our alternative hypothesis. I mentioned the conditions already. We'll assume they're met and check that off. So since the conditions are met, we're going to run a one-sample t-test. Here's how you run the one-sample t-test. This is going to be, it looks like a normal distribution, but remember, because we're dealing with means and we don't know the population standard deviation, we just have our samples. So since we don't have sigma, this is going to be a t-curve. So remember, a t-curve looks very close to a normal curve, but it's a little flatter and a little fatter on the ends. So basically, I drew something that looked normal because basically the difference is not that easy to see. So draw something that looks normal. This is going to be our t distribution. Due to our hypothesis, the mean of our t distribution should be 30. So we're assuming that the population goes at 30 miles an hour. If that's the case and we take samples out, most samples should be around 30. Every so often we'll get samples that are out here. Fewer samples will have means farther away from 30, all right, under our assumption. So that's our hypothesized mean for the population. That's the sample we drew. There's our sample mean. So our group of 23 cars came out 31, and they had a standard deviation of 4.45. So now this is how we use the information to get the t-score. So this is the t-score down here. The last piece of information I need is the standard error. So to get the standard error, remember they give you this formula, it's the standard error on the distribution of sample means is the standard deviation of our sample over the square root of the size of the sample. So 4.45 over square root 23 gives me the standard error. Now I can get a t-score because basically now I know this t-curve's mean and its standard deviation, so I can see how unusual getting this value is. Remember, when you do the t-score, you're doing it for n minus 1 degrees of freedom. N is 23, so the degrees of freedom is 22 that we'll use in the calculator. So the t-score I'm going to get is based on a t-curve that's made out of 22 degrees of freedom. We'll get the t-score now. Take your average minus the hypothesized average and divide by the standard error. I get a t-score of 1.0777. Now, I want to use that. Basically, this score is 1.0777 standard deviations away. How often does that occur? I need this area. Since this is a t distribution, make sure you use t-CDF and not normal CDF to get the area. So in the calculator, if you go to your distributions, hopefully you can see it somewhat. There you go. Notice that there is a t-CDF. It's number 6. If I go down to t-CDF, they'll ask you to input the lower, the upper, and the degrees of freedom. So let me do that right now. All right, so The lower should be the 1.0777. I want to go up to infinity, so I put in 999. And then you need to tell it what t-curve to make. I'm making one of 22 degrees of freedom. If you don't have a fancy newer calculator, that would be the input. You'd put lower, upper, comma, degrees of freedom. And now it gives me the area. So the area of that shade region is 0.146. Remember, we can think of that as a percentage. So something, if this is our assumed mean, how often do we get a result this strange or stranger, or this far out or farther? Well, the p-value comes out at 0.1464. So about 14%, 15 roughly, 14.6 I'll say, about 14.6% of the time, we'll get an exam, or if we keep taking samples of this size, if we kept taking samples of 23, we would get a result of people having a mean of 31 or greater 14.6% of the time. Now, that happens reasonably often, so this isn't evidence that the people are speeding. Even if the real mean is 30, it's possible to get this sample a reasonable amount of the time. So that's where I wrote the flash step up here. So what would our conclusion be is we have a high p-value. Now, after checking through some of those homeworks, people are kind of getting it backwards. Remember, if the p-value is high, you don't reject the null. A high p-value means the sample we got is consistent with the null. So what I'm going to say is due to the high p-value, I failed to reject the null hypothesis. What does that mean in context? It means the sample doesn't provide evidence that the cars overall are speeding. So basically, our sample's consistent with the mean. We don't think that this doesn't prove that anybody's speeding. If the population is going the speed limit, this sample could come up, and it doesn't give us any reason to believe that overall the entire population of cars is speeding. All right. So hopefully you get the logic of this. Like I said, it's very similar to the one proportion test. The major differences are in the standard error and using a t-curve instead. So if you saw that other video, hopefully the t-curve makes sense, and now it's easy to use to do these means tests. Now, once again, make sure you're aware of the difference between statistical significance versus actual importance. So we didn't get enough evidence to suggest they were speeding, but say we did. Even if the mean speed really did come out, say we had the test ended up proving that the group was speeding. If we could show, they were really going 31 instead of 30, say the whole group was instead of just our sample, if we could show, the whole group was actually going, 30.5 or 31.5 miles an hour, this still probably wouldn't be worth acting on. It wouldn't be worth, getting the police down there to pull people over and all the evidence. But, if we had come out with a sample that showed people were going 50 and maybe we made a confidence interval and the real value might have even been lower, but it was still 45, that would still be way higher. So there's a difference between statistical significance and the actual importance. So don't mistake the two. We didn't find anything. Not only was our sample not really all that big of a deal anyway, but the sample wasn't even proving they were speeding. So, but just beware of this in real life. Statistically significant means that, the test shows that the number is really different from the null, but it would be important to note, when would we be mad? I don't know how fast they'd have to be going outside the school before we'd be mad at them, but 31 probably wouldn't be it. Maybe if they were going 35 or 40, all right? Here's one for you to try. I'll put it up if you want to try it, pause it. In a moment, I'll go on and just show the answer. So basically there's EPA regulators. They suspect that salmon that they're inspecting has an unusual amount of insecticide. They take a sample of 150 and they find that there's 0.0913 ppm, means parts per million. That's how many parts per million of insecticide, whatever chemicals or molecules they find. The standard deviation of their sample comes out as 0.0495 parts per million. Now, the EPA says the average, or maybe the acceptable amount of this insecticide that's actually allowed in salmon is 0.08 ppm. So 0.08 ppm is supposed to be what they're looking for. These guys are at 0.0913. Is this suggest the company has unusually high levels? Now, I'm going to let you assume, once again, like I did, assume the conditions are met, because they would have to tell you some stuff about the conditions. We'll assume everything's independent and random. 150 is less than 10%. And the one condition, that nearly normal condition, notice that since the number is 150, it's way greater than 40. So let's just assume all the conditions are met, since I just talked through them. See if you can set up the null, get the p-value using the t-curve and that stuff, and then make your conclusion, both with whether you reject or fail to reject the null hypothesis, what that means in context, all right? So you can pause if you'd like to do that. I will just now show the answer, so let's move. So hopefully if you tried it, here's what I got. So my hypotheses, I hypothesized that the actual mean amount was 0.08 parts per million. Now, once again, this is a one-sided test. My alternative is that the mean is really greater, and then the company might be in trouble. Number two, I said, let's assume the conditions were met, so we skipped that part. Now, how will you set up your calculations? You'll set them up as follows. The t-curve here, the t-curve, and just so you're aware, if I think there's the homework I'm going to assign, they're going to ask about the distribution, like, oh, what are the parameters of the distribution or something. If they ask about the distribution, you can just say what kind of curve it is. In this case, it's a t-curve. It's going to have 149 degrees of freedom, and its parameters are its mean and the standard error. So it has a mean of the hypothesized population mean, and its standard error, the standard deviation for the sampling distribution, not for the sample itself, but for the distribution of grabbing those kinds of samples, is this, all right? So in case they ask you that. So how am I going to get my t-score? Well, basically, this t-distribution, that's its mean, that's the sample. So if I assume that these guys are following the rules, and this is the amount of insecticide in there, how often am I going to come out with a sample like this? Well, there's my n, there's my sample mean, which is greater than my hypothesized mean, and there's the sample standard deviation. I need the standard error. Standard error is 0.0040. I need a t-score using 149 degrees of freedom. I'm going to take my sample minus my hypothesized mean to see how far, if this is true, how far away it is based on standard errors. It's 2.825 standard errors away. Now I need the p-value. Is that above 5% or lower than 5%? We'll use that as the standard cutoff. We'll go to a calculator, put in TCDF, use the t-score I found. That thing is 2.825 standard deviations away. That's reasonably far, but since it's a t-curve, we want to be careful we get the right value. I used up to 999, 149 degrees of freedom. The p-value came out 0.0027. So that is a low p-value. Remember, low p-values mean the null, that this is a rare result. It's probably not, the null is probably not true. We're probably getting this rare result because the null is actually not true. This is inconsistent with the null, because basically if the null were true, it's extremely rare. I'm going to get a sample of 150 that has a mean this high. Now, it's possible, but that's how likely it is, and that's not likely at all. That's a chance of 2 out of 1,000. All right, so due to the low p-value, now here's my conclusion. Due to low p-value, I'm going to reject the null hypothesis. Rejecting the null hypothesis means they're probably not following the rule. They probably have more, and that's, their sample definitely has more, but that means the entire population of their salmon is very likely to have more. So notice that that's going to be my conclusion. The sample gives evidence that the amount of insecticide in the salmon in general is above that usual amount. So in this case, they might be in trouble. Remember, the tests can be wrong. This is unlikely to be wrong, but it's possible. This would probably flag the company, though, that they would go in and do some more detailed work to see if they really were having too much insecticide. All right. Well, hopefully you were able to get that example. Hopefully this makes sense. This is how you do a one sample t-test. I'll put the assignment online with it. And basically we're going to move on and do two sample intervals and tests. And then there's one last thing, and then the course will be over. All right, so be on the lookout for those things.